matter how small, the quantum scale or the chemical scale, right up through organisms like us and ecosystems, right up to galaxies. It's a very useful set of ideas that applies to many different kinds of systems. The metaphor that seems to be emerging for the system sciences is Gaia. And I'll tell you, Gaia is another name for our living planet. I'll say more about that very shortly. And understanding this concept of Gaia requires the system sciences. One can literally not understand what Gaia is outside of the context of system sciences. So normally I talk about Gaia second in the seminar I do, and I go to system sciences first. I want to start with Gaia and tell you just a little bit about it. The first thing I need to emphasize very strongly is that Gaia is not a religion. It's not New Age mysticism. It's a science. It's fully compatible with physics, chemistry, and biology. It is a hypothesis, now a theory, that was proposed in the early 1970s by this man, James Lovelock, British atmospheric chemist, who is 90 years old this year. And this wonderful person, Dr. Lynn Margulis of University of Massachusetts Amherst, I consider her to be a friend. I had the pleasure of spending 3 weeks with her in August of 2010 in her home and lab. Those two proposed the Gaia theory in the 1970s. This theory is extremely well supported by hypothesis testing and model building. I'll talk a little bit more about those later on. This idea is mainstream science in Britain and parts of Europe. It's taught as and studied as mainstream science there. It's had a hard time getting its foot in the door of academia here for some historical and political reasons that I can talk about later if you want. It is arguably, at least scientifically, the most important idea of the 21st century, or at least one of the top. A little caveat, a little warning caveat about Dr. Lovelock. I think that he is scientifically a genius. I think his Gaia theory is a brilliant idea. Many people don't like him because of his advocacy about certain solutions to climate change. And my recommendation is, if you don't like his solutions, set them aside. Don't pay attention to them, but don't ignore his science of Gaia. It's very important that we pay attention to what Gaia is. So I want to quote Dr. Lovelock about why it's important that we understand Gaia. This is from his book called The Revenge of Gaia, Earth's Climate Crisis and the Fate of Humanity. It's not necessarily a very fun book to read, but it's an important one. And here is one of the paragraphs from the book. Metaphor is important because to deal with, understand, and even ameliorate the fix that we are in over global change requires us to know the true nature of Earth and imagine it as the largest living thing in our solar system, not something inanimate like that disreputable contraption, spaceship Earth. Until this change of heart and mind happens, we will not instinctively sense that we live on a live planet that can respond to the changes we make, either by canceling the changes or by canceling us. Unless we see the Earth as a planet that behaves as if it were alive, at least to the extent of regulating its climate and chemistry, we will lack the will to change our way of life and to understand that we have made it our greatest enemy. Very profound paragraph, and he backs this up well with his science in this book. So let's deal with exactly what is this concept of Gaia. It is not the environment. It's a term. The environment is a term that I don't even like. It implies that it's something out there beyond us that we're really not a part of. Neither is it the biosphere, which is a more scientific term. Instead, Gaia is Earth's planetary scale homeostasis and metabolism. Now, you'll notice that I'm underlining key words here. In the seminar, we go into great detail about what these terms mean. I'm just going to give you a taste of it for this morning's lecture. Homeostasis is a scientific word from biology that refers to the collection of all of the processes in your body that maintain your temperature, your blood pressure, and the chemistry of your blood and the tissue fluids. Sugar levels, amino acid levels, hormone levels, antibody levels, the temperature and your blood pressure. That collection of processes is called homeostasis. Metabolism is the collection of all of the chemistry going on in every cell of your body. And it's quite complex. I'll show you just a little snippet here. This is one tiny little part of metabolism that goes on in all of your cells. This little cycle of chemical reactions here is called the citric acid cycle. High school biology students often have to memorize it, and they don't like it as a result. It's actually quite easy to understand from a systems perspective. Now, that citric acid cycle is part of a larger set of processes. If you're chemically squeamish, don't look at this diagram. Very complex set of interacting molecules. One becomes another, becomes another, becomes another. It's a network of chemical reactions. And the actual diagram that this is part of is probably 10 times bigger than this. And that's only a summary of the metabolism that's going on. So Gaia is Earth's metabolism and homeostasis. That is, think about your own homeostasis and your own metabolism and scale it up to the size of a planet. That's what Gaia is. Simple as that. It is composed of coupled or linked living and non-living parts. The rocks, the water, the air, the non-living parts. We and the species are the living parts, and those are interacting with each other to make up this giant planetary scale life form. Gaia automatically, without conscious intention, has regulated the temperature and chemical composition of Earth's atmosphere, oceans, soils, and even the surface rocks at conditions suitable for life for over 3,500 million years. That's 3.5 billion years. Now, I underscore the word automatically here because just like your homeostasis works automatically, you do not have to think about where your blood pressure is. It just automatically regulates. Same with your temperature and your blood sugar. Gaia does that as well. Gaia is not a conscious entity. It's not thinking about this. It does it on its own. If it's conscious at all, it has the consciousness of a bacterium. It's not a rational being. So where is this Gaia? It's not merely inhabiting the surface of the Earth. Instead, Gaia extends all the way from the upper atmosphere, 100 miles up at a place called the thermosphere, very hot, all the way down to where the crust meets the mantle, about 100 miles below our feet. Gaia is everything in between that. The whole planet, rock, water, air, life, evolves as a single living entity, but it's not an organism. It's not like you or I or a pine tree. It's a different form of life entirely, unique probably in our solar system, or so we think. Geophysiology is planetary physiology. Human physiology studies our homeostasis. Geophysiology studies the homeostasis of Gaia, planetary physiology. It is the science of how Gaia works. How does this planet regulate its temperature and chemistry over such a long period of time? It's not difficult to understand. I'm not going to talk about it in this presentation. In the full seminar we go into detail, but it involves natural selection acting on species and something called physical and physiological constraints. It's really easy to understand. It's easy enough that I can teach this to high school students. Not difficult at all. It is necessary, this idea of geophysiology in Gaia is necessary for understanding global heating or global warming and climate change as symptoms of a much larger problem, and that is the disruption of Gaia's metabolism and homeostasis. That's a much more serious problem that we haven't really begun to be aware of yet. But understanding geophysiology requires the system sciences, which I'm going to talk about next. I want to just list here on this slide some of the system sciences principles that I'll just touch on today. Be aware that all of these are actually easier to understand than pronounce. They're going to sound like foreign words, but they're really almost intuitive for most people. Networks and systems, feedback and nonlinearity, system states, critical thresholds, also called tipping points, phase transitions, where a system undergoes an abrupt change very fast, energy gradients, dissipation of energy, something called thermodynamic equilibrium, self-organization, autopoiesis, which is a fancy word for metabolism, emergence and emergent properties, system states including chaotic states and something called the chaord, and fractal geometry and power laws. Fractal geometry is a beautiful new form of geometry. It's the geometry of nature, essentially. So I'm going to go through each of these in a little bit of detail. We'll start with networks and systems, which are almost the same thing, but subtly different. Networks and systems are groups of coupled or linked interacting parts. Here, for example, is a very complex network. It's a marine ecosystem food web off the coast of Africa in the Atlantic Ocean. And if I magnify just a little part of this, you can see that this is composed of parts, the species, which are hake in this case, mackerel, snook, anchovy, herring, and the lines between them indicate the connections between the nodes. Who eats whom? And the arrow points from the ET to the eater. So you can see this complex web of who's eating whom, and that gives you the sense that networks are in a sense circular. That is, you can start from any one part and weave through the network and circle back to the original part. That's the reason they call it circular. That circularity leads to a phenomenon called feedback. That is, the actions of any part feed back through the network to itself. Now, there's two kinds of feedback in systems, and they're called negative feedback and positive feedback. And I'll hasten to add that it has nothing to do with value. One is not better than the other one. Instead, it has to do with the action on the system itself. For example, negative feedback always reverses a trend in the system. If something is increasing, negative feedback decreases it. If something is decreasing, negative feedback increases it. It reverses the trend, up or down. It stabilizes the system around something called the set point. So in this little graphic here, you can see the set point, perhaps the thermostat setting at 68. And as temperature warms up, negative feedback cools it down. If it gets too cool, it warms it back up again. It's cyclic around the set point. Negative feedback is the way heating and cooling systems work in this building and in you as well. Keeps you at 98 degrees, 0.6 Fahrenheit. Positive feedback, on the other hand, does just the opposite. It accelerates a trend in the same direction, whether down or up, whether hotter or colder, doesn't matter. And that destabilizes the system, kicks it into a new state, and it does so very rapidly, very, very fast. An example of this would be a microphone in front of an amplified speaker. Sound comes out of the speaker, goes into the microphone, gets amplified, comes back into the microphone, amplified, and you get this ear-piercing screech that's very unpleasant. That's positive feedback. Now, the relevance of this is that most climate models that are being used to study climate today do not include sufficient positive feedback processes. They're overwhelmed by negative feedback, and it makes us think that the climate is more stable than it really is. This will be a major point in part 2 of this lecture. Positive feedback, in turn, causes something that we call non-linearity. And non-linearity, I could give you a complex mathematical definition, but instead, I just want to show you some pictures. And once you see non-linearity, you're going to understand it. You'll always recognize it. A linear system, if I were to show you a graph of a linear system, you would see a straight line representation of some variable over time. Temperature, number of dollars in a bank account. It's a straight line, either flat, sloping up, sloping down, maybe vertical, but it's straight. Nonlinear systems look like that. That's anything but straight. The only straight is straight up or straight down. It's very erratic and jagged. This is 10 years of the Dow Jones stock market average, ups and downs, some little, some big. Here is another nonlinear image that I'll talk more in depth about in part 2. This is 400,000 years of data for CO2, that's the top line, temperature is the red line in the middle, and methane concentration in the atmosphere, that's the green line at the bottom. 400,000 years. Now the point to look at now is just simply the shape of the lines. It's nonlinear. It's very jagged and erratic. So this is the signature of nonlinearity. You'll recognize